So today we are going to be introduced to a tool that is super powerful. A tool that allows you to get a grip on limits that, if you were simply evaluating, would turn out to be virtually unwieldable, or at least demand a lot of additional algebraic work to evaluate precisely. So here's the deal. Say you've got a limit, and say that limit is a ratio of two things. And say whenever you plug in to try to evaluate the limit, let's just say you plug in, if x is approaching a, say you plug in a upstairs and plug in a downstairs. And say what pops out is of the form either 0 over 0 or infinity over infinity. And actually, with the infinity over infinity, it doesn't matter whether it's positive infinity or negative infinity and upstairs or downstairs, as long as you've got an infinity upstairs and an infinity downstairs. These are situations that are not directly computable. When we were back in chapter 1, we saw a lot of limits that would evaluate to 0 over 0 or infinity over infinity. And we'd have to do manipulations on the expressions using algebra, like multiplying by conjugates if we had square roots, or what other things did we use? We would add fractions together if we had fractions inside of fractions. If we had a limit that was going off to infinity, we'd sometimes multiply by 1 over the highest power of x. There were just a bunch of sort of tools and techniques and tactics that we would apply. And here's the thing though, like virtually every problem that you saw back in the time whenever you first saw it during test 1 could have been approached with L'Hopital's rule. L'Hopital's rule is super powerful. It allows you to take the functions that are upstairs and downstairs and utilize the derivative to simplify them possibly further. Now, let me be very clear about this, because it's just a fact of the matter. Like, you can't prove L'Hopital's rule and give it due justice without using some high-powered, sensitive machinery that doesn't show up until the 300 and 400 level in math. So, unfortunately, we don't have the tools, or it's not worth taking the time to develop the tools to show why L'Hopital's rule works. This is one of the rare cases where I'm just going to present to you an idea and say it is what it is because it works. If you don't believe me, take math to the 300 or 400 level, take an advanced calculus course, and you'll, see L'Hopital's rule proved, certainly. But yeah, so here's the idea. If you have a limit that is a ratio, and if that limit evaluates to something that is 0 over 0 or an infinity over infinity, then whatever the limit would turn out to be is going to be equal to whatever the limit would turn out to be when you took the derivative upstairs and downstairs. Because if you think about what derivative does, in particular to polynomial expressions, the derivative simplifies polynomial expressions because it brings the degree down progressively, successively, one derivative after another. And, this is a way to take what might be a complicated expression and simplify it down in your evaluation. The way that I like to think about this is L'Hopital's rule is like taking a limit to the hospital. Like, your limit is sick. It's giving you an output of 0 over 0 or infinity over infinity. And if we want to attempt to make the limit well, we'll run it through the limit hospital to see if the limit hospital can resolve the situation. Here is a limit that showed up at some point early on in the test 1 material. I also brought it up shortly after test 1 to prove the derivative of sine and the derivative of cosine in a video. And it was cumbersome to prove. I had to do it numerically with a lot of plugging and chugging. But here's the thing to notice. Whenever you just evaluate this, note, this evaluates to what? Well, plug in x equals 0, we'll have sine 0 over 0. Well, since this evaluates to 0 over 0, L'Hopital's rule applies. If we didn't evaluate to 0 over 0, or if we didn't evaluate to an infinity over infinity, L'Hopital's rule wouldn't apply. But hell, if we didn't evaluate to those things, we'd probably be able to much more quickly resolve the situation anyways. So now we've got a limit that is not, well, let's run it through the limit hospital. Limit, x approaches 0, derivative of sine, cosine, derivative of x, 1. And this problem is now solved because there's no longer going to be 0 in the denominator. When you plug in x equals 0 above, you get cosine 0, which is 1, and 1 over 1 is just 1. Problem solved. To resolve this limit previously, when we saw it, like back in test 1, test 2, like at the end of test 1, start of test 2, we had to use numerics. We had to plug in x's to the right of 0, like 0.1 and 0.01 and 0.001. We had to plug in values of x to the left of 0, like negative 0.1, negative 0.01, negative 0.001. And L'Hopital's rule, powerful as it may be, impossible to show as it is, boy, it cuts through that with a knife, doesn't it? What about this guy? Limit as x approaches 0 of this function. Well, if you do the evaluation, note, this evaluates to, numerator would be 1 minus 1, denominator would be 0. Well, 1 minus 1 over 0 is 0 over 0, and now we know L'Hopital's rule applies. And since L'Hopital's rule applies, well, we can give it a shot to see if taking this limit to the limit hospital works. And so we have now limit as x approaches 0, take derivative on top. Derivative on top, the 1 drops off. Derivative of negative cosine is sine. Downstairs, x becomes 1. And this limit is now basically solved. You no longer have anything in the denominator that could be 0. You've got just a good old-fashioned number. And then we evaluate upstairs, sine of 0 is 0. And this limit is 0. At the end of test 1, at the start of test 2, we evaluated this limit as well. And in order to do this limit, we plugged in values like x equals 0.1 and 0.01 and 0.001, and x is equals to negative 0.1 and negative 0.01 and negative 0.001. And L'Hopital's rule, again, cuts through this problem with a knife. And now as you look at these two examples that were cumbersome to compute previously, but sharp to compute with L'Hopital's rule, you might think, oh my gosh, L'Hopital solves every limit problem without having to think, and that would be hasty. Because there are a couple particulars related to L'Hopital's rule. I want to get into that in the next video and in a few examples. But let's keep this just in the forefront of our mind. L'Hopital's rule can make quick work of limits that otherwise would be very difficult to work with. There are cases where L'Hopital's rule becomes cumbersome and we have to be more thoughtful. It's not a mindless act, but it is a way to work through with less mess. And boy, that makes it valuable.